there. So, having done our inclining experiment, we now need to process the results in order to find out whether our ship is actually stable enough to go to sea or not. Okay, so let's just note down the information that we've got from our inclining experiment, and then we'll do some calculations in order to find out what state our stability is in. Okay, so we did our experiment by moving weights from side to side across the ship, and those inclining weights, there were 4 of them, and they were 24 grams each. The displacement of the ship at the inclining experiment, so we call that the as inclined displacement, and remember the displacement is the mass, how heavy the ship is. So at the inclining experiment we weighed our ship and we found that it weighed 1.08 kilograms, so that's 1080 grams. We used a pendulum to measure the movement of the ship. And the length of that pendulum was 105 millimeters. We took the draft. Now, we're not going to use the draft because we were able to use a scale because our ship was so small to work out its displacement. But in a real-life situation with a full-size ship, you would use the drafts to work out the displacement of the ship and so weigh it that way. So I'm going to write them down here just because they would be so important in a real-life inclining experiment. Now, if you remember, I made a slight mistake in measuring these drafts, which was just that I measured them with all the inclining gear on board except for the inclining weights, and I added them afterwards. Now, because I was just eyeballing these drafts and they're really quite approximate, I don't think it'll make a significant difference. So the drafts as inclined were 2.5 centimetres to the port side and 2 centimetres to the starboard side. So we had a bit of a significant list on during this experiment, and I expect that's just because of the gear that was on board. That boat generally floats pretty level when it's empty, so that will just be because the gear was not perfectly centred. It's not a big deal. Okay, and then we had the distance that we moved our weights in order to create that movement during the experiment. We call that the shift distance. And we measured that as 70 millimetres or 7 centimetres. Remember there's 10 millimetres to the centimetre. Okay, and then we have our actual data from the experiment. So we're going to stick that here. We're going to have a shift and then we're going to have our pendulum reading. Okay, so at the start of the experiment, pendulum reading was 2 millimetres to port. And then we'll have shift 1, 2, 3, up to shift 8, which was the final one. And if you want to remind yourself which weights were moving in which direction for each of these shifts, you can scroll back into the video and see that. Okay, so we went from 2 millimetres to port to 12 millimetres to port when we moved the first weight. Then we went from 12 millimetres to 22 millimetres to port. Then we started shifting the weights back across again. We went from 22 down to 14 millimetres to port, and then back what was supposed to be a return to the 0 point, the 0 point being with the pendulum being slightly off to port. It didn't quite return. That's normal. There are so many sources of error in inclining experiment that you expect these readings not to be perfect. That's why we take so many of them. Okay, then we started shifting our weights to the other side, and we went from 4 millimetres port to 6 millimetres starboard. Then we went out to 15 millimetres to starboard, and then we started shifting them back again, and we got 8 millimeters to starboard, and then we returned right the way back to our starting point, which is 2 millimeters to port. So you can see from the fact that every time it comes back to 0, the pendulum is slightly off to port, that the whole pendulum was, despite my best efforts, tilted slightly to the port side. That doesn't matter at all, because what we care about are actually not these absolute readings. What we care about is how far did the pendulum shift at each point. So what we care about is what we call the deflection. So you moved a weight and the pendulum deflected by a certain amount, and that's what we actually care about. So the deflection is the difference from each point to the following point. So at shift 1 it had moved from 2 millimeters port to 12 millimeters port. That's a deflection of 10 millimeters. Then it shifted from 12 millimeters port to 22 millimeters port. That's also a deflection of 10 millimeters. If the experiment was perfect, you would expect to see the exact same deflection at every step. You won't see that because the experiment is not quite 100% perfect. You go from 22 down to 14, and that is only a shift of 8 millimeters. So we can see that our average deflection is going to be a little bit less than 10 millimeters. Okay, so from 14 millimeters port to 4 millimeters port, that's 10 again. From 4 millimeters port to 6 millimeters starboard, that's 10. From 6 millimeters starboard to 15 millimeters starboard, 9 millimeters. Then from 15 millimeters starboard back down to 8 millimeters starboard. That's a shift of only 7. And then from 8 millimeters starboard to 2 millimeters port, that's a shift of 10. And if the experiment that we set up was a little bit more complicated than this, for example, if we had inclining weights which were all individual different weights, or if we had them shifting by different amounts, we would have to take a slightly more complicated approach. But as it is, we're working with 4 weights which are the same, and they're shifting by the same distance. So that means we can actually just average this deflection, and that will give us a reasonable answer. Now, there are a number of different ways of processing an inclining experiment which give us sort of, the methods become progressively more complicated, and they give us a progressively more exact answer. So if you could go right up to the extreme of actually graphing these results and then regressing in order to find the gradient of the lines in order to find the stability of the ship. We're not going to do that. We're using the most basic possible method here. So we're just going to average this deflection, and then we're going to treat it as if it was just one weight, one shift, one deflection, and that gives us a good enough result. Okay, so to average, total these all up and divide it by 8, and if you do that, you'll find that your result comes to 9.25 millimeters. So as I said, a little bit less than 10. Now, when I say we're going to calculate the stability of the ship, what we're actually going to be calculating is a quantity called GM, or the metacentric height. Now, I'm not going to get in this video into what exactly a metacenter is. We'll look at that in another video another time. But basically the metacenter is an imaginary point which tells you how stable your ship is. The higher your metacenter, the more stable it is. The lower your metacenter, the less stable it is. But it doesn't just depend on that. It also depends on where the centre of gravity is. So if your centre of gravity is higher, then your stability gets less, as is the case with anything. If you've got a high centre of gravity, you're top heavy, you're going to be less stable. So what that means is you want your metacenter to be above your centre of gravity. That's a stable ship. If it's the other way around, it's capsized. And the closer your centre of gravity gets to your metacenter, the less your stability is. So what we really care about is that distance there, and that distance is called the metacentric height. And that's what we're using to represent stability. Now, ship stability has a lot of different factors that come into it if you're going to look at it really in detail. But the metacentric height's a really good, just quick rule of thumb. What sort of stability are we looking at here? Is it good? Is it bad? Is it mediocre? And so that's what we're going to be calculating. So that's the metacentric height. And really what we're actually after, first of all, we'll work out the metacentric height, and then we'll use that to work out where's the centre of gravity. Because the metacentric height in this condition is not on its own incredibly useful. Why? Because this ship doesn't go to sea with 4 inclining weights, a smartphone holder, a pendulum, and a whole lot of extra Lego on it. All that gear is there purely to undertake the experiment. And if you were to say, oh, its stability is good or bad in that condition, you wouldn't be fairly representing what it's actually like when it's at sea. If this ship goes to sea, it goes to sea, in this case, in its lightship condition, in other words, empty with nothing on board, and then it might take on cargo from there. So we're going to work out our GM in this condition, but then we're going to have to work back a bit in order to find out what does that mean about the stability of the ship in its normal condition. Now, the metacentric height has a legal minimum for all ships of 150 millimeters. There are very, very, very few exceptions to that. So if you want to go to sea as a commercial vessel, you're going to have a metacentric height of at least 150 millimeters. So we're going to find out in the course of this if our ship is actually legal to operate as a commercial vessel. Now the formula, if you've got all this data from an inclining experiment, this is a really simple formula for working out metacentric height, and that is the GM is the mass of your inclining weight times the shift distance divided by the displacement of the ship times the pendulum length divided by the pendulum deflection. Now there's a whole lot going on in this formula. This is one of these formulas that's doing an awful lot of work for us. There's an awful lot of theory in here. In this pendulum length over pendulum deflection, there's a whole lot of trigonometry mixed up inside that. This mass times distance, that's working out the moment that has been applied by moving our weight. The displacement's in there because how big a reaction you get in terms of pendulum deflection to the weight depends on how large your ship is, so that we have to know how heavy it was in the first place. If you had a big deflection, that might not be a bad thing if the ship's relatively small, but if you had a big deflection on a big ship, you're seeing possibly a bad stability situation there. So there's a whole lot of theory in there that I'm not going into. I'm basically just bringing this out fully formed, and we're going to use it. But there's a lot in there that you might be interested to find out about another time. Okay, so we stick in, and generally speaking, the units which are used in this would be mass in tons, distance in meters, displacement in tons, and pendulum length and pendulum deflection is a ratio. So actually, as long as they're both the same unit, it doesn't really matter. They would either be meters or millimeters usually. This ship is small, so we're using mass in grams for both the mass of the inclining weight and for the displacement. And we're going to stick to distances in millimeters. What that means is it will give us an answer out in millimeters. Usually you would get an answer out this equation in meters, because you would use meters for this here. But we're going to get an answer out in millimeters. So just a word to the wise, if you see this equation being used in a full-size ship, the units will be different from what I'm using just now, because this is a miniature ship. Okay, so we're not looking at the weight of all, or the mass of all 4 inclining weights together, because remember, we averaged the deflection. So we're treating this as if it was just one movement and it produced this one average deflection. So our mass that we moved was 24 grams. Our distance that we moved it was 70 millimeters, and we're sticking with millimeters, not centimeters. Our displacement of our ship is 1080 grams. Okay, and our pendulum length is 105 millimeters, and our average pendulum deflection is 9.25. And if you sit and work out that lot, you will get, oops, that's not shouldn't be an equals, that should be a multiplication there. You will get an answer of 17.66 millimeters. Oh dear. I said the legal minimum was 150 millimeters. So this ain't looking too good. However, remember what I said, this is not the operating condition, this is the as inclined condition with a whole lot of extra weights on board, some of which are pretty high up. So let's do a little bit of calculation to see what difference those weights make to our ship's stability. Before we do that, we're going to have to use our GM in order to work out where's the centre of gravity of the ship. And this is where I'm going to do a Blue Peter and say here's one I made earlier, because I've gone away and there's a different video where I'll show you the nuts and bolts of this if you really want to see it. But I've gone away and I have worked out the position of the Metacenter in this inclining experiment. And there's a whole lot of magic maths involved in that. As I say, I'm not getting into that because that's not the purpose of this video. But I'm just going to tell you that in this condition, in the as inclined condition, the Metacenter was, wait, I've got notes here. Where's my Metacenter? There it is. 6.97 centimetres above the keel. And what that means is we've just worked out how high the Metacenter is above the centre of gravity. So here's our little ship. That's not really the shape of it, is it? It's wider and flatter than that. There, okay, there's our little ship there. There it is. This little funnel there. Okay, and this ship has a Metacenter. We'll say it's somewhere up here. And it has a centre of gravity here. And we've just worked out that the height between the Metacenter and the centre of gravity here is 17.66 millimetres. In other words, that's 1.77 centimetres. And that means that if we know that the Metacenter above the keel was 6.97 centimetres, we can subtract this from that to find out how high up is this centre of gravity. Okay, so the centre of gravity is 6.97 minus 1.77 above the keel. And that means it's 5.21 centimetres above keel. So what we want to do now is we want to take all that gear back off again and see does that make our centre of gravity a bit lower? Is that going to improve our stability a little bit? Well, let's have a look. The items that we had on board the ship which don't belong are the inclining weights, and I'm going to divide them up into two categories because if you recall, two of them were down inside the ship and two of them were sitting up on top. So we're going to say the inclining weights on the upper deck, and the inclining weights on the interior deck. And you'll see as we go on why I've divided them up like that. Then we've got, of course, our smartphone. And then we've got the pendulum. And the pendulum and all of its supporting structure. Then we've got the smartphone holder. Remember that Lego arrangement that held the smartphone so that you could see the readings on the pendulum. And then we've got all the various other little bits of Lego which were used to produce a nice flat deck structure so that our pendulum and our weights could fit onto that. Okay, and for each of these items, I noted down, I measured what the masses of all these items were. So the inclining weights on the upper deck, 2 24-gram inclining weights, 48 grams. I'm just recording all these in grams. 2 24-gram inclining weights on the interior deck, 48 grams. Then we've got the smartphone, 155 grams. The pendulum was pretty light, it was only 23 grams. The smartphone holder was 94. And the Lego deck structure was 31 grams. And if you total this lot up, you'll see it comes to 399 grams. What I'm going to do is I'm going to put all this in the form of a table where we're going to subtract this lot off of the ship. So we're going to say our as inclined ship up here, and we know that it weighed 1,080 grams, and then we're going to call these the items off. These are the things that we are taking off in order to bring this ship back to its normal condition. Okay, I'm actually going to move this lot down a little bit. I've not quite left myself enough space for my table headings up there. Okay, so these are all the items involved in this experiment, and each of these has a mass in grams. Okay, so that's fine. And we're going to say, because these items are coming off, we're subtracting them. Okay, and if you subtract this lot off of that, you get a mass of 681 grams, and that is the light ship. In other words, the empty vessel. 681 grams. Okay, and for each of these items, that's all very well, but we need to know what it does to the centre of gravity. So for each of these items, we need to know what is the vertical position of the centre of gravity above the keel. So we're just measuring up from the keel for all of these, and we're going to measure this in centimetres. You notice that I've made a slight shift from millimetres to centimetres. I'm just adjusting the unit that I'm using to give me the most handy numbers, because later on the numbers get difficult if we're working with millimetres, because they tend to give us very large numbers. So I'm shifting it to centimetres now. On a full-size ship, you would just work with metres all the time. Okay, and we just calculated where the vertical centre of gravity of the ship was relative to the keel. It's 5.21 centimetres. Each of these things, well, we made some measurements, didn't we, at the end of that video last time. So what I'm going to do is I'm going to just have a little sketch over here. So here's our ship. Okay, so this here, that line, that's the keel. And that is indeed actually a flat horizontal line on the real ship. And we've got inside, the ship has an internal deck, which a lot of these items were resting on. Okay, and we measured the height of that internal deck as being 25 millimetres above the keel, roughly. So that's 2.5 centimetres. Then it has an upper deck, where the funnel is. Okay, and that upper deck, we measured that as being 80 millimetres above the keel, so it's 88 centimetres above the keel. And our various items that we calculated that the smartphone or we estimated really, that the smartphone centre of gravity was 75 millimetres, that's 7.5 centimetres above the interior deck. Okay, so what that means is that the smartphone is its centre of gravity 7.5 centimetres above here, and that's 2.5 centimetres above the keel. So it's 10 centimetres above the keel for the smartphone. I've jumped the gun here doing the smartphone first because it's not the first thing in the list. Never mind. We'll work out our inclining weights on the upper deck then. So our inclining weights were little paint pots, and I estimated that their individual little centres of gravity were 12 millimetres above their base, so 1.2 centimetres above the base. They were sitting on a Lego platform, and that Lego platform I estimated was 4 millimetres above the interior deck, so 0.4 centimetres above the interior deck. So we've got our inclining weights which are on top of the upper deck. You've got 8 centimetres and then 1.2 centimetres. That's 9.2 centimetres above the base. And then your inclining weights on your interior deck, you've got 2.5 centimetres plus 0.4, so that's 2.9. And then you add on 1.2, and so that comes to 4.9 centimetres above the base. And you need to work this out, and this is exactly what you do on a real inclining experiment. You work out the positions of all of the various items on board relative to the keel or whatever other baseline you're using. Okay, so that's our inclining weights. Then we've got the smartphone. The pendulum is sitting on the Lego deck, and the pendulum centre of gravity is 4 centimetres. Rather, actually, it was sitting on the Lego deck, but actually when I estimated above the interior deck. So it's 4 centimetres up from this interior deck. So we're looking at 6.5 centimetres above the keel. And then we've got the smartphone holder. So we estimated that the smartphone holder's centre of gravity was 5 centimetres above the interior deck, and the interior deck's 2.5 centimetres above the base. So 7.5 centimetres for the centre of gravity of that. And then our Lego deck structure, we estimated that the centre of that was 2 millimetres above that interior deck, so 0.2 centimetres. So we've got our 2.5 centimetres and then 0.2, so it comes out as 2.7 centimetres. So these are all in centimetres. Okay, that's fine. So how do we work out, given that we know the centres of gravity of all these items individually, how do we work out the combined centre of gravity of all these items, and then how do we take it off the ship in order to find out what the real centre of gravity of the ship was before all these things were put on it? We use a concept called moments. And what I'm going to do is I'm just going to shrink this down a little bit in order to move it out of our way. So I'll shift it over here so that it's out of the way. It doesn't need to be too small. And I'm going to put in another column on our table here, which is called the moment. What is a moment? A moment is an effect which something has in order to rotate something. So go back to what I said in the very first video about ships being seesaws. If you put a weight on one end of a seesaw, that weight has an effect in causing the seesaw to rotate. And when I said if ships are not more complicated than seesaws, it's just that seesaws are a little bit more complicated than you thought they were, how much effect you get in rotating the seesaw does not just depend on how heavy the person is that you've placed on the end of it. It also depends on how far they are from the pivot point. So if you put one child on the end of a seesaw or 2 children halfway along the seesaw, that has the same effect. It creates the same moment. The effect is the weight you put on the seesaw times the distance from the pivot. That's the moment. So in this case, we're doing exactly the same thing. We're going to say, okay, so each of these items, we put it on the ship, or in this case, take it off again, and that has a certain effect on the ship. Now, it might not be as obvious as the effect of putting a child on the end of a seesaw, because you can see that rotation, but you get a similar effect on how stable the ship is, depending on not just how heavy the object is, but how high it is above the keel of the ship. So we're going to work out the moment, the effect that each of these items has on the stability of the ship by multiplying its mass by the centre of gravity. So that 1080 times 5.21, that comes to 5,626.8. And this is in grams and centimetres, so you actually just measure the moment as gram centimetres. In a full-size ship it would be ton metres. Okay, and then we take each of our items that we are subtracting off and we multiply this mass by this height of the centre of gravity again. And our answer is going to come out negative because we're removing it. Okay, so this 48 times this 9.2 comes out as minus 441.6. This minus 48 times this 4.9. I made a mistake earlier. It's not 4.9 at all. It's 4.1. If you spotted that yourself, if you were calculating along, well done. 4.1 centimetres. So that 48 times that 4.1 comes out as minus 196.8. This minus 155 times this 10 comes out as minus 1,550. This minus 23 for the pendulum times 6.5 comes out as minus 149.5. This minus 94 times 7.5 comes out as minus 705. And this minus 31 here times 2.7 comes out as minus 83.7. And what we do is we sum that lot up. Because although you can add together centres of gravities of things, that would be nonsense. It would mean nothing. You can add together moments. So if you put multiple children on your seesaw, you can add up all the weight of them, but all that tells you is how far they're pushing the seesaw into the ground. You can't add up the distances that they are from the pivot point, but what you can do is you can multiply the weight of each child by the distance, and then you can add all those up. And you need to bear in mind then that some of them are pushing it this way, some of them are pushing it that way. So there's a subtraction that has to go on. But basically you can add up moments in any situation, and it's an extremely useful thing to do. The only proviso is they have to be measured from the same place. So on the seesaw, all those moments have to be measured from the pivot. It would be no use measuring little Johnny from the right hand end. That wouldn't give you a reasonable answer at all. So it's same here, these are all measured from the keel, so they can be added and subtracted. So if you take this 5626.8 and you subtract all of these off it, you get an answer of 2,500.2. And how do you find the combined centre of gravity of the ship minus all these things? You just divide this moment by the total mass, the final mass of the ship. So you say, okay, what is our light ship? Remember, light ship's your empty ship. Vertical centre of gravity is the moment divided by the mass. So it's that 2,500.2 divided by 681. Okay, and what does that come to? That comes to 3.67 centimetres above the keel. Look at that difference. That's a huge difference. Just to remind you, the original vertical centre of gravity of the ship with all the inclining gear on it was 5.21 centimetres above the keel. Now we've taken all that gear off and we find that the centre of gravity has dropped down to 3.67. So the stability is definitely better in its lightship condition than it was in the inclined condition. And I could tell that when I was inclining it. I could tell that the smartphone in particular, being both heavy and high, was destabilising it. It was moving in a way that I could tell it wasn't as stable as it ordinarily would be. So let's find out, is our metacentric height at the legal limit or not? Well, we know the vertical centre of gravity. Do we know the position of the metacentre? Yes, we do. And again, here's one I prepared earlier. I have gone away and I've calculated where the metacentre is in the lightship condition, which is in a slightly different position from where it was in the as inclined condition. So what I can tell you is that the lightship metacentre, and again, I'll do another video explaining that calculation for people who want to get really up to their elbows in it. But the lightship Metacenter is 10.15 centimetres above the keel. So that means its lightship metacentric height is that metacenter minus centre of gravity. So it's 10.15 minus 3.67. And that comes out as 6.48 centimetres. All right, 64.8 millimetres. What did I say the legal minimum was? 150 millimetres. So I'm afraid that while this ship is stable, it's got a positive metacenter, and you can see that it's stable because it floats upright. That's the ultimate test of whether a ship is stable. It is stable. It's not stable enough to operate at sea as a commercial vessel. So I'm afraid in order to operate our ship at sea as a commercial vessel, we're going to have to come up with some kind of solution which makes this metacenter a little bit bigger. Okay, thanks for following us through that inclining experiment and arriving at our final result. I'm sorry that it's not a better result. I had hoped that the ship would meet the legal minimum, but unfortunately it is an old-fashioned ship. I'm sure you can tell by looking at it. And older vessels tended to have lower GMs. They tended to be a little bit less stable, especially passenger vessels. Why? Because the more stable your ship is, the more uncomfortable it is. And that might seem like a surprising statement to make, but it's absolutely true. And when I come out with a video on metacenter and stability and how all that works, I'll get into that a little bit more. For the moment, thank you for watching, and I'll see you next time.